Okay, so today we talked a little bit about rotational motion. And so we've been working with RMM, rotational motion model. And just to give us a little bit of context about where we are in the curriculum, we've already talked about a particular kind of rotation. If you were here at the end of class today, Thursday, then you don't have to watch this bit. You can skip forward maybe like 45 seconds until I switch to a new piece of paper. We already saw this in CFPM. An example of rotation. CFPM was circular force particle model. We talked about centrifugal or centripetal force and gravitation. Talked about how the centripetal force always points towards the center seeking. That is one example of rotation. Now, more recently, we've talked about how we can discuss rotation in terms of kinematics, and that is what the first topic is that we covered in rotational motion. Right after center of mass. So we had rotational kinematics using the relationship between angular and linear descriptions of rotational motion to solve problems. So this is rotational kinematics. Now, how does something move? It can't move unless it has a force, and so we've also more recently talked about dynamics. But now we're not talking about forces anymore as much as we are talking about torques. So you have rotational dynamics that cause rotational kinematics, but if we really want to think about more interesting situations involving rotational forces, we have to talk about two different scenarios with torques. Now we know that rotational dynamics involve torques. What happens when the net torque is equal to 0? That's what we've been talking about recently. This is called statics. And so in statics, we're dealing primarily with a situation where the net torque is 0 on an object. And we've been able to solve problems like that by using our net torque equations in clockwise and counterclockwise. Now, the other big thing that we haven't talked about yet is what happens if the net torque isn't equal to 0. If it's not equal to 0, then an object is going to move. And this isn't called statics, rather it's called moving. I can't think of a better word for it. But this is moving where you have an angular acceleration. In this case, the angular acceleration was 0. In this case, the angular acceleration is not 0. It exists. The object will be rotating. And so this is what we're going to be talking about for the next couple of days. This still fits with RMM3, but this is going to transition us into work and energy. All right, so to start us off, I'm going to go through example problem 1 on RMM3. Dynamics practice problem C. So we're flipping back a page. Now, I'm going to read this problem and draw a little sketch on this paper, and I'll walk you through how to solve this problem. All right, so we got a 15 kilogram uniform sphere. So it has a radius of 15 centimeters. First thing I'm going to do is just label the radius. R is equal to 0.15 meters. We also know that the mass of this sphere is 15 kilograms. It's a pretty big, or pretty massive, but small sphere. Interesting. Okay. About an axis, it rotates about an axis tangent to its surface at 3 radians per second. All right, so this is pretty huge. We know that it rotates about an axis tangent to its surface. It doesn't rotate at an axis about the center of the object. Rather, it rotates about an axis tangent to its surface. Okay.
So it's like that kind of. All right. Interesting.
It rotates initially at 3 radians per second. A constant torque of 10 Newton meters then increases the rotational speed to 7.5 radians per second. So this little sphere is rotating, and it encounters, initially at an angular velocity of 3 radians per second, it encounters a torque of 10 Newton meters and speeds up to 7.5 radians per second. Now the question is, through what angle does the sphere rotate while accelerating? That is theta. We want to figure out theta. All right. Now we clearly have some information here about the torque, which is analogous to force. And we have some information about angular initial and angular final velocity, which is very similar to just linear initial and linear velocity. So let's just treat this as an acceleration problem. This might as well just be a box that was being pushed and had some initial velocity, had some final velocity. You know the force. We have to find the displacement, right? Because that's what the angle here is, the displacement. So we're going to approach this in a very similar way as we would with a linear dynamics problem. All right. Now the other question is if the sphere's radius was 10, whatever. So right now we have a mass, a torque, and we want to figure out that theta. But we can't figure out that theta without knowing omega. We can't figure out omega without using a net torque equation. So we have torque and we have mass, but we know that this is a rotating object, so we can't just work with mass. We have to look at the moment of inertia. All right, so we're going to have to do a little bit of work here to figure out that moment of inertia. Now, we know that to find I, we know that we know that I parallel is equal to ICM plus MR squared. Because this object isn't rotating about its center, it's rather rotating about an axis tangent to its surface. This axis has to be distinct from the moment of inertia about the center. So we know that the moment of inertia about the center for a solid sphere is 2/5 mr squared. You can look back at your table to figure r squared.
We know here that it's going to be plus mr squared because mass is the entire mass of the sphere, and this r is actually just the radius given. So mr squared. So in the end, we end up with 2/5 plus 5/5, so we get 7/5 mr squared. It is a moment of inertia about an axis tangent to the surface of the sphere. So 7/5 mr squared. Now let us leave it in terms of m and r for now, because we know this, and then set up an equation that's going to allow us to solve for acceleration. Okay, so we also know that the net torque is going to be equal to moment of inertia times angular acceleration, right? This is very similar to F equals ma. In fact, it's the same thing, but just for rotation. Now, the torque we have, moment of inertia we have, we can hella easily solve for angular acceleration. So alpha fish is equal to torque over moment of inertia. Now, I'm going to have to switch to another piece of paper at this point. This is pretty outrageous. Alpha is equal to torque over moment of inertia. In this case, we know that the torque is a constant 10 Newton meters, and we know that that moment of inertia is, here, actually I'll calculate it over here. I is equal to 7/5 mr squared, over here 7/5 times the mass of the sphere is 15 kilograms, the radius is 0.15 meters. That squared is going to be equal to, let's see, 7/5 times 15 times 0.15 squared. All right, so we have a moment of inertia of 0.4725. Okay, 0.4725, 0.4725, and then the units are kilogram meter squared. Okay, so we have to plug this in right over here for I, 0.475 kilogram meters squared. Now, we see the meters cancel out here, so we get Newton kilogram meters. Interesting. What an interesting set of units. 10 divided by 0.475, we end up with 21.05 radians per second.
squared. Radians per second squared. All right, cool. Now, we have an acceleration. If we want to find displacement, this is pretty easy. All we need to do is use one of the good old kinematics equations, but just for rotation. The kinematics equations, but for rotation, you can also find in your packet. If you flip back to page 9, it's just these bad boys, right? So we do have omega final, we do have omega initial, we have acceleration, boom, delta x or delta theta, easy money. All right, omega final squared is equal to omega initial squared plus 2 alpha delta theta. Let's solve for that delta theta. We know that omega f squared minus omega initial squared is equal to delta theta all divided by 2 alpha. All right, now in this case, delta theta is equal to omega final squared, which was 7.5 radians per second squared, minus omega initial, which was 3.0 radians per second squared, all over 2 times 21.05 radians per second squared. We're almost done with this one. When we multiply all of this out, we get, what do we get? We get 7.5 squared minus 3 squared, all divided by 2 times 21.05. Alright, so we end up with 1.1. I think that's the correct answer with sig figs. I think that's it. Let me make sure. We should get around 1.1 radians. That kind of sucked if I just did all this work and the answer was wrong. Hey, alright, so that is our answer. Now the question is whether or not this, or if the sphere's radius was 10 centimeters, would that angle increase or decrease? So to do this, let's take a look back and see where did we actually use a radius. Over here. Okay, so over here, in order to figure out moment of inertia, if we had a smaller radius, we would have a smaller moment of inertia, right? Because as radius increases, the moment of inertia increases. So if you have a smaller radius, you have a smaller moment of inertia. If you have a smaller moment of inertia, you have more acceleration, right? Smaller inertia, same force. Smaller inertia, same force, much bigger, or not much, but bigger angular acceleration. So if we had a bigger angular acceleration, we know that the angle would, if you had a bigger angular acceleration, you would in fact increase this number on the bottom. So if the denominator got bigger here, oh, interesting. So if the denominator got bigger here, you'd be dividing by a bigger number. You would have a drop in that angle. The best way to do this is actually to look back at the work that you did. Look back at it. Look back at it. And locate where the variables of interest are. So if you increase R, I increases. If I goes up here, angular acceleration oh, sorry, I goes down. R goes down. I apologize. So if the sphere's radius was 10 centimeters as opposed to 15, this would go down. Moment of inertia would go down. Angular acceleration would go up. And then if angular acceleration goes up, right over here, angular acceleration goes up, you're dividing by a bigger number. So then this goes down. Delta theta. Alright, thank you for watching this video. Now try out problem number 2. That is all you. This isn't going to be the exact same as problem number 1, but it is going to be similar. The way that you should approach this, the big things that you should do, is draw a free body diagram for this and this. Show me the net torque about this pulley. Show me the net torque about this pulley. and with that net torque, determine what the angular acceleration is of the pulley. Alright? Word. See ya.